Hey guys, so we are going to look at exponential and logarithmic equations. So we've got these tools now. We've been playing with different rules you've seen rules for exponents and rules for logarithms. Um, and so we're just going to go through a bunch of examples of how using some of these tools to solve equations, right? One of the things we'll want to be doing with them. I've written here the properties we have, right? We've got our basic definition of logarithms in relation to exponentials, and then those logarithmic properties that we have worked on in the past. And I'm just going to go through a bunch of examples. So here's our first equation. I've got log base 2 of 1 minus 2x is equal to 3. In this case, I just need to appeal to the basic definition of a logarithm. This statement, right, if we think carefully about it, right, I'm gonna use this first, our definition of logarithm, and just notice that, right, this is my b, this is like my x, and this is like my y in this first statement over here. And with that map, using just seeing where they go, this means 2 cubed is equal to 1 minus 2x, right? That's an equivalent statement according to the definition of the logarithm. And I just evaluate 2 cubed, and now we've got a pretty straightforward algebra equation to run through. So divide both sides by -2, and we get x equals 7/2. Right? So that's a pretty straightforward case where we've got we can just straight use that property or that definition. Here's our next: 3 times log 7 of x is equal to 8. We can't quite jump in and use that definition here because the definition doesn't have a coefficient at the front, so we don't really know where it would go if we try to apply the definition. However, here I'm gonna number these things so I can refer to them. We'll call that 0, 1, 2, 3, 4. I can use property 3 here, going from the left side to the right, to rewrite this as x cubed. And now I can use property 0, or the definition, and I know that 7 to the 8th is equal to x cubed, and I can take the cube root of both sides so that I'll have x is equal to 7 to the 8/3, right? And that for me is a good enough answer. If you insist on a calculator approximation, I can do that. This comes out to be about, let's write it, 179.3. Okay. Okay, let's keep going. I'm going to just move these with us as I scroll down so we can keep referencing them. All right. So our next equation I want to solve, let's look at 3 to the x equals 7. Right, and we're going to find in many of these that there's more than one way to do it. And so if you think you have a solution that's different than mine, it might be valid if you're applying rules properly. And you end up with the same result, though it may look different algebraically. You might need to manipulate it to see that it's the same thing, or compute it to see that it evaluates to the same number. But in any event, one way we might approach this problem is just taking the natural log of both sides. And the reason I'm doing that is because the exponent that I'm trying to solve for is locked up in as the exponent. And by taking the natural log, really taking any logarithm, it brings that exponent down because of property 3, right? We can do this because of the one-to-one property of logarithms, right? That so these two values, 3 to the x and 7, we both know are positive numbers, and so those are that's right. Sorry, that's why we're able to put these in logarithms, because they're both appropriate inputs. And when we take the log of two equal things, we'll get equal things. That's not really the one-to-one property. That's going in reverse. It's just the fact that log's a function. So in any case, we take x down according to that property, and I get the natural log of 7. And then I just divide both sides by the natural log of 3. And I get x equals the natural log of 7 over the natural log of 3. Right? And again, that's something you could evaluate on a calculator. I'm going to leave that one alone. I do want to note, here's another way you might decide to solve this. 3 to the x equals 7. You might think, well, since I'm looking at exponential, I can use this the zero property here, our definition. This statement it's a little confusing because I've got x in the exponent, which was formerly played by y, but if you think through this carefully, this is log base 3. Sorry, I want to just write it on the other side. Log base 3 of 7 is equal to x, right? And that's just a direct appeal to that property 0. This does not look like the answer that I got here. However, if you note the change of base formula, property 4, you can rewrite this in terms of any base you'd like. In this case, if I choose base e, or the natural log, using that change of base formula, this becomes the natural log of 7 over the natural log of 3, which is exactly what I got. It's pretty typical for people to work in natural logs, which is the reason I did it this way. Some of that is probably just you just kind of get used to it. It shows up a lot. It's a convenient thing. It works well with calculus. There's various reasons. Some of it is probably historical because we didn't have tables for all the bases, and so you use the tables that you use the bases that you might have, or even some of the old calculators didn't compute bases outside of maybe 10 and e. But in any event, that's a pretty common thing to do, is work in natural logs, and that's what I did there. Okay. Let's keep rolling. Here we go. 5 times 6 to the x equals 12. This is a similar sort of problem, except we don't necessarily, let's do this a couple different ways. What I would probably do is divide both sides by 5 first. So 6 to the x equals 12. And then I would take the natural log again. So I'll have natural log of 6 to the x equals natural log. I forgot to actually divide by 5. The natural log of 12/5. Then take x down with our property 3. And then divide natural log of 12 over 5 divided by the natural log of 6. Right? So there's certainly other ways to do this one, but that's the way that I find most pleasing for me. Okay, let's keep going. So I'm going to use a very simple example to prepare us for a more complicated example. If I have something like 2 to the x minus 1 equals 2 to the 3 minus 2x, okay. What we have here, we know that exponentials are one-to-one functions, and so that if you have the same base if you have a base raised to powers, if they're equal, those powers must be the same, right? And it probably feels pretty intuitive that has to be true, but it's actually not always true for other kinds of functions. It's something we need to know. And in this case, for exponentials and logarithms, this is true. And it's true because they're one-to-one functions. Each output can only be gotten via one input, right? Just as a counter example, right? If you have something like x squared equals y squared, right? The squaring function doesn't have this property. This does not imply that x is equal to y. It could be the case that they're opposites, right? And certainly when you get to trig functions, this becomes even more disastrously not true, where many, you could have sine of a is equal to sine of b, and there are infinite choices for a and b being different that would make this equation true, and so we can't say that they're equal. But in the case of exponentials and logarithms, we can, and so we get to say, okay, x minus 1 is equal to 3 minus 2x. We can just move things around. to get that x is 4/3 for that to be true. Okay. Sometimes it's not quite so straightforward. Move my properties with us. All right, though I don't really need to use any of them for this immediate problem, but we'll want them soon. So a similar kind of problem to the one I just did is this. We have 4 to the x is equal to 1/8 x plus 2. And these are not in the same base. However, 4 is the same as 2 squared, and 1/8 is the same as 2 to the negative third. And then by the rules of exponents, I just multiply those exponents. I get 2 to the 2x is equal to 2 to the negative 3x minus 6. All right, so I've manipulated them to become the same base. All right, and now I can use that property. 2x is equal to negative 3x minus 6, or 5x is equal to negative 6, or x is equal to negative 6/5. Okay. If you don't notice that these can be manipulated that way, we can use our other methods. So for example, we might, if we didn't realize that, we might have taken the natural log of both sides. The x plus 2, and then we get x times the natural log of 4 is equal to x plus 2 times the natural log of 1/8. On that right-hand side, I can let's see, distribute. That's the word my brain was failing to come up with. Equals x times natural log of 4. I'll subtract the terms with x's in them, so I get x natural log of 4 minus x natural log of 1/8 equals 2 natural log of 1/8. Factor out the x, so I have natural log of 4 minus natural log of 1/8 equals 2 natural log of 1/8. And I can divide, but actually let's first just combine this using one of our properties. Natural log of 4 minus natural log of 1/8 is the same as the natural log of, it's going to be 4 divided by 1/8, which is the same as 4 times 8, so that's going to be the natural log of 32, 2 natural log of 1/8. And now I'm going to divide and say x is equal to 2 natural log of 1/8 over the natural log of 32. And let's do one more thing here, because if I bring that 2 in as an exponent, it squares the 1/8. So this becomes the natural log of 64 over the natural log of 32. These are both powers of 2. Maybe I'll leave that as an exercise. You can use this now and maybe write them as powers of 2. And what you'll be able to work out with the change of base formula. Oh, sorry, I miswrote something here, I realize. Yeah, you can work it. I'll just do it. I'll do it. Sorry, I was going to leave that up to you, but I'll do it. So, sorry, when I squared 1/8, I wrote 64. It should be 1 over 64. Let's rewrite both of these as powers of 2. This is x equals the natural log. So 64 is 2 to the 5th, so 1 over 64, or sorry, to the 6th, so 1 over 64 is 2 to the negative 6th. 32 is 2 to the 5th. Maybe you see where this is going now. We can use our property 4, property 3 to bring those exponents out front. Negative 6 natural log of 2 over 5 natural log of 2, which is just x is negative 6/5. right? Now, if we hadn't done it this first way, first of all, we got to the same answer. We may not have noticed at this step that this would work out so nicely. It depends on how familiar you are with powers of 2, whether you look at something like 1/8 and 32 and see those as powers of 2. There's certainly nothing wrong with the way we did it on the right, but you can see it was much more complicated and gives us a much more complicated answer that feels like we need to go to a calculator unless you're pretty clever with these tricks. So noticing that you can rewrite things in the same base is not a necessity, but it certainly can be a time saver. All right, let's keep moving. Let's do a different kind of equation now. Let's look at a log equation of this form. Log base 3 of x minus 1 plus log base 3 of x minus 3 is equal to 8. First, I'm going to use property 1 to rewrite this as a single logarithm, x minus 1, x minus 3 equals 8. And then we can use property 0 to rewrite this as 3 to the 8th. I feel like I meant this to be something else. So this does not look like it's going to work out super well, but that's all right. X minus 1, x minus 3, 3 to the 8th is a pretty big number, right? And now at this point, so 3 to the 8th is a pretty big number. I'm certain that I meant that to be something else, but I'm not going to worry about it. But we can still do this, or we at least set it up to see how we would solve this. On the right-hand side, I can expand this. I've got x squared minus 4x plus 3, which I can rewrite as 0 equals x squared minus 4x plus 3 minus 3 to the 8th, right? And this is now a quadratic. This is a quadratic, and we're probably not going to be able to factor it because because of this being the wrong number. But we always have the quadratic formula. So notice in this, the way I have it written, we've got an a is equal to 1, b is equal to negative 4, and c is equal to 3 minus 3 to the 8th, right? And so we can find the solutions to this as x equals negative b, so 4 plus or minus the square root of b squared, so that'll be 16 minus 4 times a, which is 1, times c, which is 3 minus 3 to the 8th. All right, notice 3 minus 3 to the 8th is going to be a negative number, right? 3 to the 8th is large, and all of this is going to be over 2a. And so we can rewrite this a little nicer. X equals 4 over 2 plus or minus. In the square root, notice there's a factor of 4 and a factor of 4 for both of these. So that can come out of the square root as a 2, leaving behind 4 minus 3 to the 8th over 2, which we can cancel all those 2 now. So we have 2 plus or minus the square root of 4 minus 3 to the 8th. Okay, so let's just think about these two results. This is going to be 4 plus some large number. Let's compute that really quick. So 3 minus 3 to the 8th. So what I'm getting is, let's see if this has a, all right, 4 minus 3 plus 3 to the 8th. Put this in the square root. So if I take the square root of all that, I'm getting something that's, we'll just call it 81. It's pretty close to 81. So x is approximately 2 plus or minus 81. All right. Now let's just think about those two results. 2 plus 81 is about 83. 2 minus approximately 81 is going to be a negative number. right? We know, and then when we look at our original equation, putting in a large negative number here and here will give us a large negative number, which is not acceptable to log. And so one of our solutions is what we call extraneous. The only solution that we can actually take is the one that's 2 plus 81. This should be approximately, right? That's the only solution that actually works for us. And this happens sometimes. There's nothing wrong with that, right? We get two possible solutions to this equation, but one of them doesn't work for our original function, so we have to toss that one out and stick with the one that's left. Okay, let's do two more and we'll call it good. So let me grab my properties again. Let me grab these properties and drag them along with us as we go. And let's see, the next one, our second to last one, is going to be 5 to the x plus 1 is equal to 6 to the 2x minus 1. It's okay, I can have a visitor. Here, come here, buddy. You're gonna watch me do math for a minute. Okay, math. So how do we solve this? So we're gonna take the natural log of both sides. 5 to the x plus 1, right? We coming up with a common base between 5 and 6 is going to be an awkward number. So a much better thing to do, I think, is just take our natural logs. Again, we see that our exponent, or our variable that we're solving for, is tied up in the exponent. The logarithm is the thing that gets it down. And we use the, really any base will work here, but the natural log is a pretty typical one to work in. All right, now I have to expand this in order to get those x's together, right? There's an x on both sides locked up in parentheses. X, that's right, plus the natural log of 5. On this side, we get 2x times the natural log of 6 minus the natural log of 6. So I'm going to take everything with an x to the left-hand side, and everything without an x I'll get on the right. So on the left, we're going to have x times the natural log of 5 minus 2x natural log of 6 is equal to the negative natural log of 6 minus the natural log of 5. I can factor out an x on the right-hand side, on the left-hand side. So we have the natural log of 5 minus 2 natural log of 6 is equal to negative natural log of 6 minus natural log of 5. And then divide. So x is going to be equal to negative natural log of 6 minus natural log of 5 over natural log of 5 minus 2 natural log of 6. And this is perfectly acceptable. This is a good answer. I might simplify it a little bit. I'll let you figure out how I'm doing this. If I multiply, well, I'll say it. I'll let you work through the steps if you don't see it. I'm going to multiply the numerator and the denominator by -1. That gets rid of the negatives on the bottom. It switches the order of my subtraction here. At the same time, whoops, that should be subtraction. At the same time, I'm going to take that 2 natural log of 6 and bring that exponent inside the 6 to square the 6 to get 36. I don't know. Maybe that's a better way to write it. I'm not sure. It seems like it takes maybe slightly less symbols. In any event, they're equivalent. Okay, and again, that's a calculator problem. If you really want to have a decimal answer, an approximation, you're free to plug all that into your favorite calculator. I'm going to go ahead and leave it as is. All right, last one. It's a different kind of equation. If we have 4 to the x minus 2 to the x minus 20 equals 0. So this is a thing that happens in all kinds of cases. You'll see it in trigonometry where you have what I would say is something like this is quadratic in an exponential, meaning an exponential is playing the role of x, right? In general, when we have a quadratic, we're talking about something like ax squared plus bx plus c. When we have we're setting it up in this kind of equation. What I mean by a quadratic in this exponential, let's rewrite this a little bit. 4 is 2 squared to the x minus 2 to the x minus 20 equals 0. then I know that this is the same as 2 to the 2x minus 2 to the x minus 20 equals 0. And I can rewrite this first one, again, using the rules of exponents. Right? And we have something of the form that we have right here. We have a thing squared, that same thing not squared, and then a constant, right? With some coefficients, right? In this case, there's coefficients of 1, -1, and then 20. And I can treat this thing and do the same things I do with a quadratic. For instance, if I had the following, if I had y squared minus y minus 20, I could factor this as y minus 5 y plus 4. Well, if 2 to the x is what's playing the role of y, the same thing applies. So we have 2 to the x minus 5, 2 to the x plus 4 equals 0. Right? And we use the same rule we use when we solve these kinds of equations, that if the product of these two things is 0, one of the following must be true. Either 2 to the x minus 5 is equal to 0, or 2 to the x plus 4 is equal to 0. Right? On the left, we get 2 to the x equals 5. And on the right, I get 2 to the x equals -4. However, we know that there's no exponent we can put on 2 to get a negative number. So that is another one of those extraneous solutions. We can throw that one away. It's not possible. And so to find to see what 2 to the x equals 5 is, I could just use property 0, but I'm going to go with my habit of using natural logs, and so this becomes x natural log of 2 equals natural log of 5, or x equals natural log of 5 divided by the natural log of 2. And that's something you can plug into a calculator to get an answer. Okay, that's it for this one. There's lots more ways we could orchestrate and design some equations, but in general, we just have to be familiar with our properties and make sure we're applying them properly. You can see these are I would call fun problems because they mix a whole bunch of skills together, but that can also be frustrating because it's not always clear what route you should take. The best solution to that is just practice. Okay, good luck, everybody.